Okay, this is the worksheet for 2G in the Math 4 course. So most of this we're going to wind up plugging stuff into Desmos and watching what happens. So that I'm going to shrink and bring over here. And I've already got the linear and the quadratic plugged in from the last thing I was doing. So I'm just going to leave it there. And we're going to plug in. I guess I need to move this over a little bit more. Well, I got to get the rest of that. There's that. All right, so I'll be typing some things that you won't necessarily see. 946, 956, 967, 991, 1003. And then I'll move over to the other side and type the 126, 104. Whoops, that's not 104. 93.5, 84.9, 44.4, 30.6. And then we'll drag this thing back over to where we can see some of it. And so what is the R value? Which you're not going to have an R value for a quadratic. You're going to have R squared for both, yes, but R value is for linear only. And so what does this tell you about the relationship, correlation? If the R value, well, I guess it would be nice if I had a pen to write with. All right, if the R value equals negative 0.9924, then I would call this a strong negative correlation. And then the best fit linear equation would be y equals negative 1.24x. And the other term that is just off the screen is 1274.36. All right, so that's our best fit linear. And of course, that's what it's going to look like on the graph and over here on the left side. Now, here's where we're going to need to use the graph to make predictions. For instance, 980 kPa, that's what we typed in as our x's. So they're asking the question, what happens when x is 980? So we got to bring over our graph and we got to get it back here to where we can see what we're doing. All right. There is our graph. Now 980, and we want not the black one. Well, that's right, we do want the black one. We want the linear one. So I'm going to grab it somewhere up there, and I'm going to drag it down here until I find 980. Almost there. There, no. I can't quite, well, maybe if I zoom in a little bit. Black line, 980, oop, there it is. 980, and the Y value is 61.382. 61.382. So we're going to come over here on this guy and say 61.382. Now, when I look at the wind speeds, they are no bigger than 1/10 or 1 decimal place. So I'm going to say that the wind speed is about equal to 61.4 knots. Again, when in Rome, do's the Romans. You know, if my wind speeds are no more precise than 1 decimal place, then that's where I'm going to round. Now, 110 knots would be the Y value. So if 110 was Y, what would X be? So I got to go back over here. and say what happens if 110 is y. That would be up here. And then we have to drag it down a little bit. 110 is y. Oh, just a little bit past it. Maybe I need to zoom in a little bit more. 110 is y. Oh, past it. And it may be that I don't get it exactly on 110, 110.21, and my next notch down is 109 point what? 110.025. That's not bad. I think I can live with that. So if that's 110, then my y value is 940.7. 940.7. So I noticed that over here, all of my air pressures are all in whole numbers. So we're going to list it as 941. And that was rounded, so I'll put the dot over the equal sign like that. All right. Now we've got another problem where we need to see if there is any way that I can, yeah, there we go. That's what I needed. And maybe scoot this over a little bit more. All right, so on our chart, we need 17, 30, 35, 47, 50, and 55. And then up here, 196, 149, 149, 174, 173, 182. So, and the question here is, now oh, good grief. Tell me I didn't just do that. I got this to where I can't get it out. There we go. All right, so use the R-squared values to determine whether it's best linear or quadratic. That's what we were after. So I've got both my linear and my quadratic set up here. I do have the table in there. So we can look at our R-squared of linear is 0.001. That's horrible. That's like no relationship whatsoever, hardly at all. And then, of course, down here, R-squared is 0.8694. So quad is going to be better. R-squared equals 0.8694. And the equation would be down there in the corner. No, that's the upper one. Negative, oh, that's right, that is quadratic. So this is going to be positive 0.11 x squared minus 8.10 x plus 298.71. That's going to be the equation. Now, 41-year-old, that's the x category. That's the x column. So I'm going to bring this guy back over here and say, by the time I get this all together, back where we can see everybody, and we're doing the quadratic instead of the linear. So what happens when x is 41? I probably need to zoom in a bit more. Oh, grabbed it on the first try. 41, and that is 153, 152. should be easy enough to remember. 153, 152. That's not what I wanted to do. I always jot it down before I forget it. Now, round to the nearest hundredth, which would be 2 decimal places. So our time would be 153.15. And let's see. That is time in minutes. Okay. Of course, that's what the graph is going to look like. Now, what happens if they run time of 171? What do you think their age is going to be? Well, so what happens when y is 171? Y is 171, which is come on. There we go. 49.96. 49.96. We're going to come back here in a minute. So the nearest tenth would be 50.0. Now, I want you to notice something about this. There is also a y is 171 over here at 23, age 23. Age 23. Well, they did have an age 17. So you actually had both. According to this data, you could have had a 171 either here or over here, at 50 or at 23. Just on the data that is available right now. That's curious. All right, last one. We have a corruption score and we have a GDP per capita. So let's plug that into our little chart and see what happens. And of course, this there. Okay, and then here. All right, so there are those figures in. So we're asked to do the same kind of thing. Look at the R-squared values. R-squared for linear is 0.908. Here it's 0.9719. So quadratic is best with R-squared at 9719. Our equation is going to look like 11.65x squared minus 452.514, I'll just call it 51x, plus 7279.97. So that's what our equation will look like. And the thing was that, we really were, when you look at the graph, the linear and the quadratic really were close to each other because the linear is following along one edge of the quadratic. one end of it, as it were. Now, let's do this out on a full thing. All right, we need, what is a corruption score of 38? What would the GDP look like? So X is 38. All right, this thing is going to be in the thousands, or 10,000s. Yeah. So a GDP of 38, and we want the quadratic. Now, as all right, we're along in there. Oh, good grief. X is 38. This is going to go on forever. 33, 34, 36, 37, 38. All right, right about in there. 38. There's 38, 6907, 253. When X is 38, Y is 6907, 253. 6907, 253. 6907, 253. So to the nearest dollar, it would be 6907. Now, when the GDP is 17,000, that was the Y value, what would X be? If the Y is 17,000, that means we're going way up the scale. 17,000 is up here. And I want, the linear and the quadratic are close to each other on one side of the quadratic. And so I'm going to zoom in, and there's 17,000.352. I don't think I'm going to get it much closer. 54.228 for 17,000. 54.228. That's not what I wanted to do. 54.228. So that means that they're to the nearest whole number, the corruption score would be about 54. Yeah, I think that was it. Yeah, that is the end of the worksheet.